Hi guys, welcome back to Data Every Day. Today we're looking at a data set of house sales in King County, USA, and it has a bunch of features about different houses, and we're going to be trying to predict the price of a given house. And to do so, we're going to use both TensorFlow and PyTorch. So this is my first time using PyTorch in one of these videos, so I'm just going to go over a basic way to create a neural network similar to how we do it in Keras or TensorFlow. So I have the task for today: given data about house sales, let's try to predict the price of a given house. Alright, I'm going to import NumPy and Pandas, of course, and then for pre-processing we're going to use the standard scalar and train test split functions function from sklearn, and we're getting TensorFlow and PyTorch, and I'm also including torch.neuralnetwork.nn as nn and torch.nn.functional as f. So we're going to import those, and let's load in the data using pandas.readcsv, and we can get the file path right over here, paste that in. Alright, and take a look at the data. So let's start pre-processing, and let's actually get a little info on the data set. I'm just trying to look to see what we want to do with this data set. I notice that we actually are missing some columns. So I'm going to go into the console and type pandas.setOption max columns and none. This way I can see all the columns at once. And now we can see we have 21 columns. The ID column is not going to help us, right? So why don't we just go ahead and drop that, because that's not giving us any useful information. So we're dropping ID from the column axis, and I'll look at the data again down here. We can see that everything is numerical, right? So we don't need to encode anything, except that we see the date is not. The date has this t, but we really want to construct two new features out of it, which will be month and year. And to do so, let's say we get just the date column. We can apply a lambda function to it that will take in some x, which will be a given date, and return just the first 4 characters of x. So you'll see we can just strip off just the year from the date. And so let's make that our new year column. Similarly, we can create a month column by, instead of indexing from 0 to 4, we'll index from 4 to 6. And we'll just get these ones. So when we're done with that, we can drop the original date column from the column axis, and our data should now look like this. We don't have a date column, but we now have a year and month column. Alright, fantastic. So I'm looking around at these. I just want to make sure I'm not overlooking something. I noticed that zip code is actually not numeric in the traditional sense. Zip code doesn't mean something different depending on how large or small it is. If we feed zip code in the way it is right now, we'll actually, our model will come to think that low values of zip code correspond to something, and high values of zip code correspond to something else, which that's not really the way this should be interpreted. So let's take a look at how many unique values we have in zip code. So I'm going to hit .unique on it, and I want to get the length of that. That actually doesn't look so bad. So in a data set of 21,000 examples, only 70 unique zip codes are present, which means I can probably one-hot encode the zip code column so that we have 70 new columns added on. And so I can do that by creating a function called one-hot encode. I'll take in a data frame, a column, and a prefix to use. So I'm going to start by creating a copy of our data frame, df.copy. And then I want to construct the dummies columns from pandas.getDummies. We're getting the dummies for the column, and we also want to include the prefix that we specify in the parameters. Alright, and then we're going to concatenate, so df equals pandas.concat, the original data frame and the dummies data frame, and that's on axis 1. And then we will drop the original column from which we created the dummies. Alright, then we'll return data frame, And one hot encode, if we pass in data, the column is zip code, and why don't we just give it a prefix of zip? If that becomes our new data, then we should see we now have 90 columns with all these zip code one hot columns, but the original zip code is gone. And now we're at a good spot, except there's one more thing I notice, which is that the year renovated column has a lot of zeros. And because year renovated is not, the 0 does not mean year 0, it means null value. But the problem is, if we feed this into the model, it's going to think that this just means a really low value of year. So let's take a look at how many of those, entries in year renovated are actually 0. We can query the data frame using data.query, and we'll query using year renovated equals 0. And you can see there are 20,699 entries in which year renovated is 0. So let's see how many we have where it's not 0, and only 914. So this is equivalent of a column with only 914 non-null values, which is just far too many non-null values to use that column. So we're just going to drop year renovated. So data.drop year renovated axis 1. Now if we take a look at data, we have 89 columns, but now all of our features are pretty good to use. So let's go ahead and scale the data. So before we do that, I'm just going to split it into an x and y. X will be our features, our feature matrix that we'll use to make our predictions, and y will be the labels, in this case price. So y is going to be data sub price dot copy, so a copy of this column, and x is going to be data dot drop price from axis 1 dot copy. So I'm just making copies of this column for y and then the rest of the data frame for x. Alright, I'll then create a scalar. Here, let me just mark this down a little. Splitting and scaling. So we'll create a scalar object that comes from the standard scalar from sklearn. And we're just going to set x equal to scalar.fitTransform x. So this will give each column in x mean 0 and variance 1. Now we're going to split into train and test sets. So xtrain, xtest, ytrain, ytest. And I'm actually, because we're going to be doing this in both TensorFlow and PyTorch, I'm going to, well, let me just, there should be a train test split on x and y, give it a train size of 70%, and we'll include a random state of 1. Alright, so because we're training in PyTorch and TensorFlow, it's important to know that PyTorch requires the objects to be PyTorch tensors. So these we could think of as our TensorFlow tensors, even though we're going to pass them in as NumPy arrays in the case of xtrain and xtest, and Pandas series in the case of ytrain and ytest, which works fine with TensorFlow. So I'm going to go ahead and call this tf_xtrain, tf_xtest, tf_ytrain, and tf_ytest. So now we have those, and let's go ahead and start training with TensorFlow. And so this is very similar to what I usually do, which is we're just going to set up a very simple neural network. So an input layer that takes, we got to check the shape of tf_xtrain. So .shape. And we have 15,000 examples and 88 features, so I'm going to pass in a vector of length 88 there. Actually, this should be shape equals. And then I'm going to create two hidden layers. One will be, so I'll call it hidden. Is going to be tf.keras.layers.dense with 64 activations and an activation function of ReLU. And I'm going to pass in inputs. Then I'm going to grab another one of those, except pass in hidden this time. Then for outputs, I'm going to return a single value in a dense layer with a linear activation, which really means no activation, and pass in hidden. Then we'll create our model, so I'll call it TF model equals tf.keras.model, passing in the inputs and outputs. Okay, then we'll compile the model, and I'm going to use an atom optimizer and a MSE loss. Alright, then we'll train the model. History equals model.fit. So we're training it on the train set here, xtrain, ytrain. And we'll include a validation split. Let's make it 12%. And a batch size. How about 32? And let's just train for 10 epochs. I'm not going to go so hard with optimizing the model here. Oh right, this should be TF model and TF model. And xtrain is not defined. Oh, sorry. This should be on TF xtrain and TF ytrain. All right. So we have large loss. I think if we can, we're going to measure it with RMSE, so root mean squared error. So we just take the square root of the loss evaluated on the test set. So let's go ahead and say TF model dot evaluate x test, actually TF x test and TF y test, and then we're going to, let's see, we have to take the square root of this. So numpy dot square root to get the RMSE value, and we'll call it TF RMSE, and we'll save that for later. We can't see what the square root is yet. Okay, now we're going to do it with PyTorch. So say training with PyTorch. And now in PyTorch it's a little different. We're going to create a class for a neural network. We'll call it net, and it's going to inherit from the neural network.module from PyTorch. And we're going to give it an initializer function that is going to inherit from its parent. And we're going to create the layers here. So we're going to call layer 1. It's going to be neural network.linear. So really that just means a dense layer. We have to specify the inputs and the outputs. So our input length is 88. Our output length is 64, because we have one layer with 64 activations. Then we have layer 2, which is neural network.linear with 64 inputs and 64 outputs. That's our second hidden layer. And then we'll call an out layer, which will be nn.linear, but with 64 inputs but only one output. And then we have to create a feed-forward function called forward. That takes in some vector x, which will be a feature vector. And x is going to be f. This is from the nn.functional package. And f.relu is going to basically just apply ReLU activation on layer 1. But we're passing x through layer 1 and then applying a ReLU activation to it. So the same thing we're doing in TensorFlow. Now we'll do the same thing except for layer 2. And then we will return self.out, which is our output layer, passing in x again. So we'll just return that. Alright, and that's it. We create a net object. And if we want to take a look, we can actually view the parameters of our model. Turn that into a list. You can see these are all the parameters for each layer. So this is the parameters for the from the weights from the input to the first layer, and these are the biases that get added after to those. And then here are the weights from the first hidden layer to the next hidden layer, and here are the biases for those. And these are the weights from the last. Oh, sorry, are we missing one here? 1, 2, 3, 4, 5. No, look, oh yeah, okay, here's our final output. So you can see we can actually, here, why don't we, I'll just paste this in. We're going to take a look at the shapes of each parameter size. So you can see we have 88 inputs, and then we add some biases, then we have that next layer, we add some biases, and then we have the output layer, the output weights that returns that single value for us. So what I'm going to do is create new versions of xtrain and xtest for PyTorch. So the reason is we need them to be torch tensors. TF-xtrain is right now a NumPy array, right? But TF-ytrain is not. It's actually a Pandas series. So why don't we, okay, let's use torch.tensor to create it to make it into a tensor. And then .type to give it a float 32 type. Alright, so this is good to feed into our model. So let's call that torch xtrain. So we're going to do the same thing for xtest. I'll just replace all these with test. And then for the y, we actually need to make it into a NumPy array first. So now we're doing torch ytrain, but we have to use numpy.array on it before. And we can do the same thing for ytest. Alright, now we have our inputs and outputs, and we can create our optimizer, which will be torch.optim.atom. We're using the atom optimizer, and we're going to pass in the parameters from our network. Parameters, and give it a learning rate of 0.01, which is the default for TensorFlow anyway. Then a criterion, which is really just a loss function, which will be nn.mse loss. So we're using the same optimizer and loss function that we use for TensorFlow. Now we're going to train in a loop for x and target in the zipped torch xtrain and torch ytrain. We're going to zero the, so optimizer.zeroGrad is going to zero the gradients for optimizer, to reset it, and then we're going to create an output which is net of x. So we're literally passing in, okay, this is iterating through our train set and our test set. And the x, which will be a single feature vector, is going to be sent through net. And the great thing about PyTorch is that it has something called AutoGrad, which tracks any functions that are performed on the input in the loss function, so that you can call loss.backward later to perform the backpropagation automatically. So loss is going to be criterion, and this is just evaluating the loss between two values, which will be evaluating between output and our target. Then we will do the backpropagation, and we will step the optimizer by one step. So we'll run that, and that's going to loop. It's doing a one full forward pass through the training set, and then I believe it's stochastic gradient descent, so it's performing backpropagation after each iteration. And then what we're going to do to get our total RMSE, we'll create total loss is going to be 0. And then for every x and target in zip torch xtest, so this is the test set, and torch ytest, we're going to make a prediction. So net of x, again we're passing in a vector, but this time it's in our test set. And then loss is going to be the criterion of output and target. So just the same as we had in the training loop. But instead of updating the optimizer here, we're just going to add that loss to total loss. And then we can get an average loss when we're done, which will be total loss divided by length of xtest. All right, and we can get the just like we got the TF RMSE here. So let's run that. That's just going to give it. Oh, sorry. This should be torch xtest. This will tally up all of our loss and then get the average of it, and we get torch RMSE, which will be average loss, right? This will be, we want to get the square root of it. We'll use torch.square root here. And then we have to detach it, which means stop tracking the gradients on it before we turn it into a NumPy value. Alright, and now let's view the results. Let's see how they perform together. Side by side. So we'll print TensorFlow RMSE and TF RMSE, and then print PyTorch RMSE and print torch RMSE. And you can see from the looks of it, PyTorch is doing better. It's very interesting. So let me just indent this. Oh, too much. No. Okay. So yeah, looks like PyTorch did better. I didn't really go into model optimization here. I just wanted to do a quick demo of how to use PyTorch, and I'm just learning it myself. So if you guys know anything about PyTorch and you'd like to help me out, feel free to leave any comments in the section below. I will definitely be using it in the future. It's very cool, and it seems a lot more flexible than Keras because it is not so high level. But that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content. And again, leave any comments you have in the section below. So I'll see you guys tomorrow. Have a fantastic day.